Welcome, everyone. I'm excited to kick off today's presentation with our first slide, Internet Protocol. Today, we'll explore the fundamental technology that makes our digital world possible. We'll cover what Internet Protocol is, how it works, and why it's so essential for communication across networks. So, let's dive in and get started. Let's talk about reserved IP addresses. These are specific IP addresses that are set aside for special use cases and are not assigned to individual devices or networks in the usual way. They serve important functions within network infrastructure and management. For example, certain addresses are reserved for private networks, which means they're not routable on the public internet, allowing organizations to create internal networks safely. Others are reserved for loopback purposes, which help devices communicate with themselves for testing. Recognizing these reserved addresses helps us understand how networks are organized and maintained securely and efficiently. Essentially, knowing which IPs are reserved helps us avoid conflicts and ensures proper network operation, which ties into the bigger picture of network design and security. Let's talk about reserved IP addresses. These are special ranges of IP addresses that are set aside and not used for regular devices on a network. They serve specific roles that help keep networks running smoothly and securely. For example, you might be surprised to learn that the IP address 192.168.1.1 is often reserved for the router in a home network. This means that it's a designated address that helps the router identify itself within the network. Recognizing these reserved addresses is important because it helps us understand how networks are organized and managed behind the scenes. Overall, reserved IP addresses play a crucial role in maintaining network stability and security, supporting the overall theme of network management and infrastructure. Let's talk about reserved IP addresses and why they are so important. Reserved IP addresses help prevent conflicts on our networks and ensure that certain network tasks can be carried out smoothly. For example, private networks can use specific IP ranges that don't overlap with public IP addresses, which helps keep everything organized and avoids confusion. Testing environments also benefit from reserved IPs because they can simulate networks without affecting or disrupting the actual internet connections. And then there are multicast and loopback addresses. They serve very specialized functions within network operations, like handling specific types of data transmission or testing the network itself. So, overall, reserved IP addresses are fundamental for maintaining a stable, secure, and efficient network infrastructure, which ties into our broader theme of understanding how networks are managed and optimized. This slide doesn't contain enough information. That's why we're moving to the next slide. Now, let's take a closer look at unicast, broadcast, and multicast, three fundamental methods of data transmission in networks. First, unicast is probably the most common. It's a one-to-one communication where data is sent from a single sender directly to a single receiver. Think of it like sending a personal email. Next, broadcast involves sending data from one sender to all possible receivers on the network at once. It's like shouting in a room where everyone can hear you. Finally, multicast falls somewhere in between. It's a one-to-many approach, but only to a specific group of receivers who are interested in that particular data. This is efficient because it avoids sending multiple copies of the same data to everyone. Connecting these concepts to our overall theme, understanding these transmission methods helps us grasp how data flows efficiently and securely across different types of networks, shaping the way we design and manage communication systems today. So, when I mention the term cast here, I'm referring to a flow of data or a stream of packets that is being transmitted from the sender to the receiver over a communication channel. This is essentially how information travels in a network, allowing devices to communicate effectively. Now, this cast is fundamental because it represents the actual data exchange that keeps our systems connected and functioning. Today, I want to take a closer look at some specific examples of cast in the field of computer networks, so we can better understand how this concept plays out in real-world scenarios. Let's take a moment to look at the cast involved in this project. This slide highlights the key people who are driving the initiative forward. As you can see, Understanding who they are is crucial because their roles and expertise really shape the direction and success of what we're working on. The cast includes a diverse group of professionals, each bringing unique skills and perspectives. Recognizing their contributions helps us appreciate the collaborative effort behind this effort. Ultimately, the strength of our team is what will enable us to achieve our overall goals. So I encourage you to pay attention to the roles and expertise these individuals bring to the table. Now, let's talk about unicast. This type of information transfer is really useful when we have just one sender and one receiver involved. Think of it as a one-to-one communication. For example, imagine a device with the IP address 10120 that wants to send data packets to another device with the IP address 201242 in a different network. That's where unicast comes into play. It's actually the most common way data is transferred over networks. So, in essence, unicast is all about direct, targeted communication between two specific devices. Let's talk about unicast. Unicast is a communication method where data is sent from one sender to a single receiver. It's like making a phone call to one person. You have a direct, point-to-point connection. This approach is essential when you need to target a specific device or user, ensuring the data reaches only the intended recipient. In the context of network communication, unicast is the most common method for everyday internet activities, like browsing websites or sending emails. It highlights the importance of precise delivery in network design, especially when privacy and accuracy are critical. Overall, unicast plays a fundamental role in how we communicate directly and efficiently over networks. So, what do we mean by broadcast? Well, in networking, broadcasting refers to sending data from one source to all devices within a network. It's a way to distribute information efficiently when everyone needs to receive the same data. Now, broadcast transfer techniques can be categorized into two main types. The first one is limited broadcasting. Imagine you have a stream of packets that needs to reach all devices on your local network. Limited broadcasting is perfect for this situation because it allows you to send data to all devices within that specific network segment without affecting other parts of the network. This approach is particularly useful when you want to ensure that every device receives the data, but you don't want to flood the entire network or reach devices outside your local environment. It's an essential concept because it helps us understand how data dissemination works efficiently within local networks, which ties into the overall theme of effective communication in networking. Now, let's talk about broadcast. Broadcast refers to the process of transmitting data, signals, or content to a wide audience, often simultaneously. It's a fundamental concept in communication technology, enabling us to reach large groups of people efficiently. Whether it's television, radio, or online streaming, broadcast plays a crucial role in how information is shared broadly. One key point to remember is that broadcast is designed for mass communication, meaning the message is intended for many recipients at once, rather than targeted to individuals. This makes it especially powerful for disseminating news, entertainment, or important messages quickly and widely. Additionally, understanding broadcast helps us see the bigger picture of communication networks and how different systems work together to deliver content seamlessly. It ties into the overall theme of effective information sharing, whether for commercial, educational, or public service purposes. So, in essence, broadcast is about connecting with a broad audience efficiently and effectively. Now, let's talk about direct broadcasting. This is a really useful method when a device in one network needs to send a packet stream to all devices across another network. Instead of sending individual messages to each device, it broadcasts the information so everyone can receive it at once. To do this effectively, the system translates all the host IDs, which helps in directing the broadcast to the right group. An important point here is the use of the direct broadcast address, which is specified in the datagram header. This address essentially tells the network, "Send this packet to all devices," making the process more efficient. This concept ties into our overall theme of how networks manage communication efficiently, especially when the goal is to reach multiple devices simultaneously. So, understanding direct broadcasting is key to grasping how networks handle widespread data transfer. Now, let's talk about limited broadcasting. When we refer to local or limited broadcasting, we're talking about a special broadcast address, which is 255.255.255.255. This address is used specifically to send traffic to all devices on the local network segment. Essentially, it's a way for a device to send a message that everyone on that local network can receive. This is particularly useful in situations where you need to reach all devices quickly, such as during network initialization or for certain types of network discovery. So, the key point to remember is that 255.255.255.255 acts as a broadcast address for all devices on the local network, allowing for efficient communication within that segment. Understanding this helps us grasp how devices can communicate effectively in a local network environment. Let's talk about multicast. So, what do we mean by multicast? Well, in multicasting, you have one or more senders and one or more recipients participating in data transfer traffic. It's a method that sits between unicast, which is one-to-one communication, and broadcast, which is one-to-all. Multicast allows servers to send a single copy of a data stream, which is then efficiently routed and replicated to all the hosts that have requested it. This approach helps optimize network resources, especially when multiple users need the same data, like live streaming or software updates. It's a key concept because it balances efficiency and scalability in data transmission. Let's talk about multicast now. When we use IP multicast, it's not just about sending data to multiple receivers. It requires support from other protocols to function properly. One key protocol is IGMP, the Internet Group Management Protocol, which helps manage and control group memberships. Without IGMP, routers wouldn't know which devices want to receive multicast traffic. Additionally, multicast relies on specialized routing protocols designed for this purpose, ensuring that data efficiently reaches all group members. Now, an interesting point is that in classful IP addressing, Class D is specifically reserved for multicast groups. This means that multicast addresses are part of the Class D range, which helps distinguish them from unicast or broadcast addresses. Connecting this to our overall theme, understanding these supporting protocols and address classifications is crucial because it highlights how multicast is integrated into the broader IP network infrastructure, allowing for efficient group communication. All right, let's test our understanding with a quick quiz. The question is, which communication method sends data to a single, specific destination? Now, think about the options. Is it broadcast, multicast, unicast, or anycast? The key here is to remember that unicast is the method used when we want to send data directly from one device to just one other device. It's like a one-on-one conversation. Broadcast, on the other hand, sends data to all devices on the network, which isn't targeted to a specific destination. Multicast sends to a selected group, but not just one. And anycast is a bit different. It delivers data to the nearest or best destination among a group. So the correct answer here is C, unicast. This concept is fundamental because understanding these different communication methods helps us design and troubleshoot networks effectively, ensuring data gets where it needs to go efficiently. All right, let's test our understanding with a quick quiz. The question is, which communication method sends data to a single specific destination? Now there are 4 options here. First, broadcast, which actually sends data to all devices on the network, so that's not the right answer. Next, multicast, which targets a specific group of devices, but not just one. Then, there's unicast, which is designed to send data directly from one device to exactly one other device. Finally, anycast, which sends data to the nearest or best destination among a group of potential recipients. So, the key concept here is that unicast is the method used when you want to send data to a single specific destination. It's all about point-to-point communication, which is fundamental for many network applications. Remember, understanding these different methods helps us grasp how data travels across networks and how different protocols are optimized for different scenarios. All right, let's talk about subnetting. Subnetting is essentially the process of dividing a larger network into smaller, more manageable parts called subnets. These subnets are like mini networks within the bigger network, and they help us organize and optimize network traffic. When we create a subnet, we're defining an internal address that combines a small network segment with a host segment. This way, each subnet has its own address range, making it easier to control and secure communication within the network. Understanding subnetting is crucial because it improves network efficiency and security. By breaking a large network into smaller subnets, we reduce congestion and isolate issues more effectively. This concept ties into our overall theme of network management and optimization, showing how thoughtful design can make networks more scalable and easier to maintain. Let's talk about subnetting and supernetting. Subnetting is essentially a way to break down a larger network into smaller, more manageable pieces. It's like dividing a big city into neighborhoods. In subnetting, we increase the number of network bits, which helps us create these smaller subnetworks. Now, supernetting is kind of the opposite. Instead of focusing on smaller networks, we combine multiple networks into a larger one. Here, we increase the host bits, which allows for a bigger address space. To implement subnetting, we often use variable length subnet masking, or VLSM, which gives us flexibility in how we divide the network. On the other hand, supernetting is typically done through classless interdomain routing, or CIDR, which helps us aggregate addresses more efficiently. Both techniques are crucial for effective IP address management, and understanding them helps us design scalable and efficient networks. Now, let's delve into subnetting and supernetting, two essential concepts for efficient IP address management. Subnetting is all about dividing a larger network into smaller, more manageable segments. This helps improve security, reduce congestion, and optimize the use of available IP addresses. Think of it as slicing a big pie into smaller pieces so each piece can be used more effectively. On the other hand, supernetting is kind of the opposite. It's about combining multiple smaller networks into a larger one, which simplifies routing and reduces the size of routing tables. This is especially useful when you want to aggregate addresses for better route summarization across your network. Both techniques are crucial for efficient network design and management, especially as networks grow and become more complex. They help us make the most of our IP resources while maintaining clarity and control over our network architecture. And ultimately, they tie back to our overall goal, creating scalable, secure, and efficient networks. Let's talk about some of the key advantages of subnetting, starting with effective IP address use. When we subnet a large network, we're essentially dividing it into smaller, more manageable pieces. This helps us make much better use of our IP addresses. Instead of wasting addresses on unnecessary or unused parts of the network, subnetting allows us to allocate IPs more precisely. This means organizations can assign IP addresses based on their specific needs, whether it's for a small department or a large office. Overall, this approach reduces wastage and makes our network infrastructure more efficient, which is a crucial goal in managing modern networks effectively. Let's talk about some key advantages of subnetting. Subnetting can really help reduce network congestion, which means it makes the whole network run smoother and more efficiently. By breaking up a large network into smaller, more manageable subnets, we can improve the way routing and switching are handled. This not only speeds up data transfer, but also makes it easier to control network traffic. So, in essence, subnetting enhances overall network performance and gives us better control over how data flows within our network infrastructure. This is a crucial concept as we look at ways to optimize network design and management. Now, let's talk about one of the key advantages of subnetting: increased network security. Subnetting allows us to implement security measures more precisely, which is a big plus. By dividing a network into smaller, manageable subnets, organizations can control access more effectively. This means we can set up specific rules for each subnet, restricting or allowing traffic as needed. Additionally, isolating different subnets from one another helps prevent unauthorized access or potential threats from spreading across the entire network. Essentially, subnetting gives us a way to enhance security by having better control and isolation within our network infrastructure. This idea ties back to the overall theme of optimizing network management and security through smarter design. Let's talk about one of the main disadvantages of subnetting, which is complexity. While subnetting offers many benefits, it can also make network configuration and design more complicated. Especially in larger networks, choosing the right subnet sizes, planning IP address ranges, and managing routing between subnets can become quite challenging. It requires careful planning and a good understanding of network architecture. This added complexity can sometimes lead to errors or misconfigurations, which can impact network performance and security. So, while subnetting is a powerful tool, it's important to be aware of these potential challenges as we incorporate it into our overall network design. Now, let's look at some of the disadvantages of subnetting. One key point to keep in mind is that subnetting requires more administrative work. Whenever you need to add new subnets or modify existing ones, it can become quite involved. This isn't just about creating new segments. It also means maintaining accurate routing tables and making sure that all subnets stay properly connected. Another important aspect is managing IP address ranges. As your network grows and changes, keeping track of which addresses belong to which subnet can become complex and time-consuming. So, while subnetting offers many benefits, it's essential to be aware of these administrative challenges that come with it. This helps us understand the trade-offs involved and plan accordingly when designing and managing networks. Let's talk about the advantages of supernetting. Essentially, supernetting allows us to combine several smaller networks into one larger network block. This is a powerful way to simplify network management. By doing so, we reduce the size of the routing table, which makes routing more efficient and faster. Plus, it helps us make the most of our IP address space, avoiding wastage and ensuring better utilization. Overall, supernetting is a key strategy for creating scalable and manageable networks, fitting perfectly into our broader goal of efficient network design. Now, let's take a look at some of the disadvantages of subnetting. While subnetting can improve network organization and security, it does come with its challenges. For example, routing can sometimes become more complex because you need to manage multiple smaller networks. However, there's a silver lining. By combining several smaller networks into a larger one, known as a supernet, we can simplify routing. This approach reduces the number of routing updates and entries in the routing table, which makes the network more efficient. Fewer entries mean less overhead for routers, helping them process data faster and more effectively. So, although subnetting has its drawbacks, understanding how to optimize network design with supernets can really improve overall routing performance. This concept ties back to our goal of creating scalable and efficient networks. Now, while subnetting offers many advantages, it's also important to understand its disadvantages. One key point is that supernetting, which is essentially the process of combining multiple subnets, can actually help improve network performance. How does it do that? By reducing the number of routing lookups needed for packet forwarding. Fewer lookups mean that the router doesn't have to search through as many routes to find the best path for a packet. This can lead to faster packet processing and, as a result, lower latency in the network. So, in essence, supernetting can make the network more efficient by streamlining routing decisions. But of course, like any technique, it has its limitations, which we'll explore further as we continue. One of the main disadvantages of supernetting is the loss of network granularity. When we use supernetting, we're essentially aggregating multiple smaller networks into a larger network block. While this simplifies routing and reduces the size of routing tables, it also means we lose some of the detailed control we had over individual networks. This loss of granularity makes it more challenging to implement fine-grained network management, security policies, and traffic control. For example, if you need to block or prioritize certain traffic at a very specific level, supernetting can make that more difficult because you're working with a larger, aggregated network rather than individual, smaller ones. To clarify, granularity refers to the scale or level of detail in a set of data. So, in this context, higher granularity means more detailed control, while lower granularity, which results from supernetting, means less detailed control. In the bigger picture, understanding this trade-off helps us weigh the benefits of simplified routing against the potential downsides of reduced control. It's a key consideration when designing or managing large networks, especially in environments where security and precise traffic management are critical. Now, let's talk about some of the disadvantages of supernetting. One major concern is the increased risk of network failures. When a single supernet experiences a failure, it doesn't just affect one small network. It can impact multiple smaller networks that are part of that supernet. This interconnectedness means that a problem in one area can have a wider-reaching effect. Another point to consider is that troubleshooting and isolating issues become more complex with supernetting. Since multiple networks are combined into one large supernet, identifying the exact source of a problem can take more time and effort. These are important factors to keep in mind when designing or managing networks that use supernetting, as they highlight the need for robust monitoring and fault isolation strategies to minimize downtime and maintain network stability. Let's talk about some of the disadvantages of supernetting. One of the main challenges is limited flexibility. Supernetting requires careful planning and coordination because the network addresses need to be compatible when combined into a supernet. This means you can't just arbitrarily change individual subnets without considering the impact on the entire supernet. In essence, making independent modifications becomes more complicated, which can reduce agility in network management. So, while supernetting offers benefits like simplified routing, these limitations can pose challenges, especially in dynamic or rapidly changing network environments. It's important to weigh these factors when deciding if supernetting is the right approach for your network. Now, let's talk about some of the disadvantages of supernetting. One of the main issues is limited flexibility. Supernetting requires careful planning and coordination to make sure that the combined networks have compatible address ranges. This means you can't just randomly merge networks without considering these details. Because of this, making independent changes to individual subnets within a supernet can be quite challenging. Any change you make to one part of the supernet could potentially impact the entire network. So, while supernetting offers benefits in terms of aggregation, it also introduces constraints that can limit how flexibly you can manage your network infrastructure. Understanding these limitations helps us see why supernetting, although powerful, needs to be implemented thoughtfully within a broader network design strategy. Let's take a closer look at the subnet mask. A subnet mask is a 32-bit number that helps us divide an IP address into two key parts. The first part is the network ID, which identifies the specific network the device belongs to. The second part is the host ID, which uniquely identifies individual devices within that network. Essentially, the subnet mask acts like a filter, telling devices which part of the IP address refers to the network and which part points to the specific device. This is crucial for efficient routing and communication within and between networks. By understanding subnet masks, we can better manage IP addressing and ensure our network traffic flows smoothly. This concept ties back to our overall goal of understanding how devices communicate effectively over complex networks. Let's take a closer look at the subnet mask. The subnet mask is a crucial part of IP addressing because it helps us determine which part of an IP address refers to the network and which part refers to the host. Think of it as a filter that separates the network from the device-specific part of the address. When we apply the subnet mask to an IP address, it allows devices and routers to identify whether another device is on the same local network or if it needs to communicate through a router to reach a different network. Understanding subnet masks is essential for efficient network design and management, as it affects how we segment networks and assign IP addresses. So, in essence, the subnet mask works hand in hand with the IP address to enable proper data routing and network organization. Let's talk about subnet masks. Subnet masks are essential because they help us divide a large network into smaller, more manageable subnetworks, or subnets. This division improves the overall efficiency of the network, making data transfer faster and more organized. It also enhances security by isolating parts of the network, so sensitive information stays protected. Additionally, subnetting boosts performance by reducing congestion and limiting broadcast traffic. Throughout this presentation, we've seen how network segmentation plays a crucial role in optimizing your network infrastructure, and subnet masks are a key tool in achieving that goal. Let's talk about why we use a subnet mask. Imagine we have a Class A network, which means it can support up to 16 million hosts. Now, managing such a vast network can be quite challenging. For starters, maintaining it becomes a huge task because of its size. Ensuring security is also complicated. Think about a company with 4 different departments. They all need access to the same network, but at the same time, they need to keep their data separate and secure. That's where subnet masks come in. They help us break down a large network into smaller, more manageable parts, making it easier to handle both maintenance and security. So, in essence, subnet masks are a key tool in efficiently managing large networks and safeguarding sensitive information across different departments. Let's talk about subnet masks and how they help us solve common network problems. The solution here is subnetting. Essentially, subnetting involves dividing a large network into smaller, more manageable parts called subnets. Think of it like splitting a big city into neighborhoods to make things easier to organize. Each department or team within an organization can have its own subnet, which not only improves security by isolating different parts of the network, but also boosts efficiency. By doing this, we reduce congestion, make management simpler, and enhance overall network performance. So, in the context of our presentation, subnetting is a key technique that helps us optimize and secure larger networks by breaking them down into smaller, more controllable segments. Let's talk about the subnet mask. A subnet mask is a 32-bit number that plays a crucial role in network communication. It helps us divide an IP address into 2 main parts, the network ID and the host ID. Think of it as a filter that tells devices which part of the address refers to the broader network, and which part identifies individual devices or hosts within that network. This separation is essential because it enables efficient routing and management of IP addresses across a network. By understanding and correctly setting the subnet mask, we ensure that devices can communicate effectively within their network and with other networks. This concept ties into the overall theme of network organization and IP management that we've been exploring. Let's take a closer look at how subnet masks are represented. A subnet mask is essentially a 32-bit number, and you can think of it as a series of ones and zeros. The ones are used to identify the network portion of an IP address, while the zeros specify the devices or hosts that are part of that network. In this example, the subnet mask is written as 111111111111111111111111111000000, which might look a bit complex at first glance. But when we translate it into the more familiar dotted decimal notation, it becomes 2552552555192. This representation is important because it helps us understand how network segmentation works and how devices are grouped together. Recognizing these patterns allows us to efficiently manage and secure our networks, which ties back to the broader theme of network organization and security. All right, let's move on to a quick quiz to reinforce what we've learned. The question is, what is the primary purpose of subnetting? Now, think about the options. Is it A, combining small networks into larger ones? Well, not quite, because subnetting actually does the opposite. Or is it B, dividing a network into smaller subnetworks? Yes, that's correct. Subnetting allows us to break down a large network into smaller, more manageable segments. What about C, increasing the number of host addresses? Actually, subnetting often helps optimize address space, but it doesn't necessarily increase the total number of hosts. And finally, D, simplifying routing tables. While subnetting can help simplify routing, the main goal is about dividing networks for better management and security. So the key point here is that subnetting's primary purpose is to divide a network into smaller subnetworks, which improves network organization, security, and performance. This concept ties back to our overall theme of efficient network management. All right, let's see how well you've been paying attention. Here's a quick quiz question for you. The question is about a key concept we've been discussing, and the answer options are listed here. The correct answer is B, dividing a network into smaller subnetworks. This process is also known as subnetting, and it's a crucial technique in network management. It helps improve efficiency, security, and performance by breaking down a large network into more manageable parts. Remember, understanding how to divide networks effectively is fundamental to designing scalable and secure networks. So, keep this concept in mind as we move forward with the next sections. All right, let's see how well you understand subnetting. Here's a quick quiz question for you. When we're subnetting, what happens to the network bits? Do they get converted into host bits, or are they moved towards the left? Or perhaps they stay exactly the same, or maybe they combine with SuperNet bits. Think about how subnetting works. Remember, the key idea is that subnetting involves borrowing bits from the host portion to create smaller networks. So, the network bits, in fact, stay the same in terms of their position, but are used differently depending on how we subnet. The most important thing to take away here is that network bits don't change their fundamental role. They're not converted into host bits, nor do they move left or combine with SuperNet bits. They remain part of the network address, just with a different subnet mask. So the correct answer is that they remain unchanged. Keep that in mind as we move forward in understanding subnetting techniques. All right, let's take a look at this quiz question. The question is asking about what happens to data during a specific stage in the process. The answer, as indicated, is that they are converted into host bits. Now, this is a crucial point because it highlights how data is transformed into a format that the host system can understand and work with. Converting data into host bits ensures that the information is compatible with the host's architecture and can be processed correctly. This step is fundamental in data communication and networking, as it allows different systems to interpret and use the data effectively. Remember, understanding this conversion process helps us grasp how data moves seamlessly across various parts of a network or system. All right, let's test your understanding with a quick quiz. The question here is, what is a key advantage of subnetting? We have 4 options to consider. First, reducing the size of routing tables. This is important because smaller routing tables mean faster and more efficient routing. Second, simplifying the routing process itself, which can make network management easier. Third, efficient use of IP addresses, helping us maximize our address space and avoid wastage. And finally, combining multiple networks into one, which isn't really the goal of subnetting, but more of a different network design approach. Now, think about which of these options really captures the main benefit of subnetting. The most critical advantage is that it helps us make our routing tables smaller and more manageable, especially as networks grow larger. So, the correct answer here is A, reducing the size of routing tables. Keep that in mind, because understanding this benefit ties directly into how subnetting improves network performance and scalability. All right, let's take a look at this quiz question. The question is asking about the main advantage of a particular practice. The answer here is option C, which is efficient use of IP addresses. Now, why is this so important? Well, in network management, IP addresses are a limited resource. Efficient utilization means we're making the most out of the addresses we have, preventing waste and ensuring better network scalability. This ties back to our overall theme of optimizing network resources and maintaining a sustainable, well-organized infrastructure. So, focusing on efficient use of IP addresses helps us maximize connectivity and reduces the need for unnecessary address space, which is crucial as networks grow. All right, let's move on to a quick quiz to test our understanding. The question is, which of the following is a disadvantage of subnetting? I'll give you 4 options. First, reducing the size of routing tables. Second, simplifying the routing process. Third, efficient use of IP addresses. And finally, combining multiple networks. Now, think about what subnetting actually involves. It's mainly used to organize large networks into smaller, manageable segments. It helps reduce routing table size and makes routing more efficient, which are benefits rather than disadvantages. So the tricky part is, which of these options could actually be seen as a disadvantage? Remember, subnetting can sometimes add complexity to network management, especially if not planned properly. But in this case, the correct answer is D, combining multiple networks, because that's not a typical advantage but could complicate network design. This question reminds us that while subnetting offers many benefits, like better IP, address utilization, and streamlined routing, it also has its challenges. It's important to weigh these when designing network architectures. All right, let's see how you did with this question. The correct answer here is B, increased administrative overhead. When we implement certain processes or systems, one of the common challenges we face is that it can actually lead to more administrative work, not less. This means more paperwork, more coordination, and potentially more delays if not managed carefully. It's important to keep this in mind because, while some changes aim to streamline operations, they can sometimes have the opposite effect if not thoughtfully designed. So, understanding this helps us weigh the pros and cons of different strategies in our overall approach. All right, let's test your understanding with a quick quiz here. The question is, what is a major benefit of supernetting? Now you've got 4 options to choose from. First, option A is enhanced network security. While security is always important, supernetting isn't primarily focused on that. Next, option B is reduced routing table size. This is a key benefit because by aggregating multiple networks into a single supernet, we can significantly cut down on the number of routes that routers need to store and process. Moving on to option C, better IP address conservation. Although supernetting helps make efficient use of IP space, the main advantage isn't just conservation, but more about simplifying routing. Lastly, option D is simplified subnet management, which can be true, but again, the most significant benefit relates to routing efficiency. So the correct answer here is B, reduced routing table size. This concept ties back to our overall theme of optimizing network performance and scalability through efficient IP addressing techniques. All right, let's see how well you followed along. The correct answer here is B, reduced routing table size. This is a key benefit because, by implementing this approach, we can significantly cut down the amount of information each router needs to store. Smaller routing tables mean faster lookups and less memory usage, which is especially important in large networks. This ties into our overall theme of optimizing network efficiency and scalability. So remember, reducing routing table size helps improve performance and manageability as networks grow larger. Now, let's move on to a quick quiz to test our understanding. The question is, which of the following is a disadvantage of supernetting? Is it increased network congestion? Or perhaps a loss of fine-grained network control? Could it be higher IP address wastage? Or maybe complex subnetting requirements? As we discussed earlier, supernetting helps simplify routing and reduces the size of routing tables, which is great for efficiency. However, it's important to recognize that there are trade-offs. For example, one of the disadvantages is that supernetting can lead to a loss of fine-grained control over individual subnets. When you combine multiple networks into a supernet, you lose some of that detailed control. This can impact situations where precise subnet management is necessary. So, think about this carefully. While supernetting streamlines routing, it does come with certain disadvantages, like the loss of detailed control over smaller network segments. Let's see which option matches that concept. All right, let's take a look at this quiz question. The question asks about a key consequence, and the correct answer is B, which is loss of fine-grained network control. Now, what does that mean in the context of our overall discussion? Well, when we talk about network management, having fine-grained control allows us to customize and optimize traffic, security policies, and resource allocation very precisely. If that control is lost, we can't make those detailed adjustments anymore. This can lead to less efficient networks, increased vulnerabilities, and a reduced ability to adapt to changing demands. So, this point highlights how crucial detailed control is for maintaining a robust and flexible network infrastructure. Remember, this ties back to our broader theme of balancing security, performance, and manageability in network design. Thank you so much for your time and attention today. I really appreciate your engagement throughout this presentation. Remember, the key points we've discussed highlight the importance of understanding the core concepts and how they connect to the bigger picture. It's all about applying these insights effectively to achieve our goals. I hope you leave here feeling inspired and equipped with new ideas to take forward. Again, thank you for being such a great audience.